Take a piece of aluminum foil, crumple it into a tight ball, and drop it in water. It plummets straight to the bottom. But if you take that exact same sheet of foil, same weight, same amount of material, and leave it flat, you can fold it into a shape that actually floats. The real question is, how much weight can a single sheet of foil support? If we start piling on pennies, how many will it hold before the water takes over and it finally sinks? To find out, we are going to test two completely different boat designs against each other to see which one can handle the heaviest payload. Because when it comes to the physics of water, what a material is made of matters a lot less than how you shape it. If you look closely at the sunken foil ball and a flat floating foil tray, the critical difference is their surface area. This cross-section shows our flat foil boat. Spreading it wide displaces a large amount of water, which responds by pushing back up against the bottom. That upward push is buoyancy, the invisible force fighting gravity to keep the boat afloat. This is exactly why a massive steel cruise ship doesn't sink. Its wide hull displaces a tremendous volume of water, creating enough upward force to counteract thousands of tons of steel. So if we want our thin sheet of foil to support a heavy stack of pennies, our first priority is maximizing its surface area to generate as much buoyancy as possible. We'll start testing with a wide, flat raft design to maximize that surface area, and compare it against a slightly smaller boat built with tall, folded walls. Dropping pennies onto the flat raft starts out strong. 1, 2, 3, 4, 5. The wide surface area holds up perfectly. But if you pile too many pennies onto one edge of the raft, the entire structure tilts dangerously toward the water. To keep the boat balanced against the water's upward push, you have to distribute the weight of your payload evenly across the entire surface. Even with perfect balance, the flat boat completely floods at 16 pennies. A wide shape gives you great buoyancy, but it offers zero structural defense against water spilling over the edges once the weight pushes it down. Moving to the walled boat, we need to apply that exact same strategy, carefully spreading the pennies across the entire bottom to maintain balance. As the weight increases, the boat sinks lower and lower into the water, yet it safely passes the 20 penny mark without flooding. This diagram illustrates exactly why. The vertical gap between the water level and the top edge of the wall is called freeboard. Those tall walls provide enough freeboard to hold 26 pennies before the water finally breaches the edge and sinks the boat. Surviving a heavy payload requires a two-part engineering strategy. You need a wide base to create buoyancy against gravity, and tall, tight walls to guarantee enough freeboard as the heavy payload pulls you down into the water. In engineering, a sunken boat is never a failure. It is valuable data. We take what we learned from both tests to design a superboat, combining a wide surface area with tall, protective walls. Before you build yours, let's test the physical forces at play. First, which shape displaces more water to float best? A dense ball or a wide flat boat? The wide boat. Second, to prevent your boat from tilting under pressure, do you stack your payload in one corner or spread it out? You spread it evenly across the hull. Finally, what structural feature gives your boat freeboard to stop water from spilling in? Tall vertical walls. Here is your ultimate engineering checklist. Change the shape to create buoyancy, spread the weight to maintain balance, fold tall walls to guarantee freeboard. Now it's your turn. Grab a single sheet of foil, a tub of water, and a stack of pennies. You have the science. Now let's see if you can engineer a boat that beats our 26 penny record.